Hello, welcome to Electronics Education. I'm Vincent Chang. Thanks for coming to the lecture. In this lecture, I'm going to teach you a kind of a challenging subject in the practical operational amplifier. And I have developed 3 lectures to focus on just this topic. Slew-rate of integrated circuit operational amplifier part 1. Rated output voltage explained. So I don't want to jump into the slew rate definition and try to explain the cause of the slew rate without giving you some of the foundation, like the transfer characteristic and the so-called rated output voltage. It just reminded me that when I was a college student, I really have no idea what's the definition, what this subject is about, what's the cause. I have no idea. And I started to teach. But at the beginning of my teaching career, I still didn't really understand the meaning behind this. So personally, I believe the best way to learn, if you want to learn, is to teach. And the best way to teach is to learn, continue to learn. Ideal operational amplifier model. You're supposed to be very familiar with this. Voltage control, voltage source. But the voltage is the differential. The difference between non-inverting and inverting. And A is called open loop gain. So based on this model, it tells us a linear relationship between the single-ended out and the differential in, right? So if you try to plot this, the vertical is output voltage, horizontal is differential input, then what do you get? You're going to get a straight line, right? Like this. And the slope reflects the differential gain of the op-amp or the open loop gain of the op-amp. But think about what's the typical value of A? What's the typical value? I mentioned this in the previous 2 lectures. 100 decibel. 100,000. That's big. That's huge. Such a huge slope. But there must be a ceiling, right? There must be a ceiling. This is the linear region. This equation only fits in the linear region. But there must be another region called saturation region, where the output voltage reaches a limit. 100,000. What about 1,000 volt? What about 1,000 volt? You're gonna get shocked, right? You're gonna shock. So there must be a limit, a ceiling. This ceiling is called positive rated output voltage, denoted by V capital M. V capital M. And then on the other direction, if you go on the negative direction, this is the positive saturation. But if you go on the other direction, then you are going to get a saturation on the other end. And you're going to reach a negative rated output voltage denoted by V lowercase m. So this is the transfer characteristic. It's the large signal. The keyword is not transfer characteristic. Output versus input supposed to be transferred. So the keyword is large signal. As the large, we're talking about volt. Large signal. And then let me give you some clue. So if you look at the product information for this Texas Instrument bipolar op-amp, then it tells you the supply voltage range from 9 volt to 15 volt. Positive, negative 9 volt to positive, negative 15 volt. In other words, if you supply voltage 5 volt, it's not going to work. If you put 50 volt, the chip cannot endure. So here's the supply voltage range. And this is the circuit diagram. I won't go to the detail, okay? Just give you some big picture. So look at 15 volt. Let's assume 15 volt and negative 15 volt. And these things are, because this is the subject of analog integrated circuit. So before you can deal with this subject, and you need a lot of foundation. First, you need some of the semiconductor physics, and then from physics to device. On device, you go to like the bipolar MOS device, and then you start to know how to analyze transistor circuit on the time-independent part, DC, versus alternating current, AC. So-called small signal, then you know how to analyze the amplifiers, small signal amplify, small signal analysis within the medium frequency range. And then you need to know how to analyze the high frequency and low frequency. And then you need to learn about the feedback and then stability, etc. Put all those knowledge together, then that's the subject called analog integrated circuit. So I'm not going to go to it's going to take some time to build block by block, build your foundation. But I do want you to know that I just want to show you the result. What result? Without teaching you the analog integrated circuit, the only tool I can use is the simulation. So the simulation result versus the model, the simple model. This is the model, right, that we have. Let's try to simulate and ask computer to do this. So just pay attention to the scale. On the horizontal is the microvolt. 400 is a microvolt. It's very, very tiny. It's very, very small. But the vertical is 20, negative 20 to 20 volt. Here's the outcome. Remember, our applied voltage for the op-amp is 15 volt, negative 15, positive 15. So where is the ceiling? For the positive ceiling, it's negative 14.2. A negative rate of voltage is negative 13.2. So several things you need to pay attention. Number one, the rated voltage is gonna lower than your supply voltage, but approach to your supply voltage. Number two, positive and negative saturation voltage sometimes, actually most of the time, is not symmetric. It's not symmetric. It's not going to be the positive 14.2 and the negative will be negative 14.2. It's not the case. So this is the simulated result for this internally compensated integrated circuit operational amplifier. There's only one or two learning objective, the major takeaway. The first, linear region, saturation region. The second takeaway is the saturation voltage is what we call the rated output voltage. As for the detail to analyze how to get the 14.2, that's the subject of analog integrated circuit design. In the next lecture video, I'm gonna, based on this rated output voltage, the concept, the large signal transfer characteristic concept, and move on to explain the cause of slew rate. Thanks for watching.